All right, this video is going to talk a little bit about probability, only we're going to talk a little bit more about sort of where probability gets a little bit trickier, not just the basics of what do you want divided by what could happen, but what will happen if we talk about the words and or. They're kind of a big idea when it comes to probability. So at the beginning of this video, though, take a few seconds to think about these questions on the page. If you're picking one card from a standard poker deck of cards, if you don't know about a poker deck, on the right-hand side there, we've got the details of a standard deck. 4 suits, again, diamonds and hearts being red, clubs and spades being in black. And then we've got 13 types of cards in each suit. So an ace, king, a queen, and 2 through 10 in all 4 suits. What would be the probability, again, the chances that you get what you want versus anything you could possibly draw? Getting a club, a heart, a diamond, or a spade, a face card or an ace, and a jack or a diamond. Think about those facts, and we'll be right back with you here in a second. All right, let's take a look at what we've got here. So the probability of a club, again, is the basics of probability. We're going to say there's 13 clubs divided by 52 total cards, and basically that means that to draw a club, there's a 1/4 chance. Kind of makes sense. Again, there's 4 suits. We're drawing one of the suits, so 1 out of the 4 suits. Kind of makes, again, complete sense there. The same idea goes for drawing a heart, a diamond, or a spade. Well, again, if we're going to look at it as a heart, a diamond, or a spade, basically we want to add up all the possibilities that we have. What you're going to hear me say a lot in this video is the words or typically mean add. Or means add. So again, we can have the probability of a heart being 13 out of 52, diamonds being 13 out of 52, or spades 13 out of 52, or basically kind of like clubs, it's a 1/4 plus a 1/4 plus a 1/4. We end up with 3/4. We're okay with drawing any one of the 3 out of the 4 suits. Now, there is another way to take a look at that one, if we wanted to. We can use the idea of what's called the complement. To draw a heart, diamond, or spade just means that we don't want, right? Don't want a club. And if you remember, if the probability of clubs is 1/4 up here, then what we want to do is take 100% of the things that can happen, or 1, minus 1/4 of the things, right? That 1/4 minus the clubs, and 1 minus 1/4 would have been 3/4. So one way to do it is add up the things you want. Another would be out of 100%, out of everything that can happen, subtract the things you don't want. Again, that's called the complement. Down here at the bottom, part C, the face card or an ace. Well, this time, again, there's 12 face cards. There's 4 aces. Basically, there are 16 cards out of the 52 cards that we're okay with. Again, or means add. But now, in that case, you got to be a little bit careful. Think about this idea down here at the bottom. If we want to draw a jack or a diamond, well, there are 4 jacks in the deck. There are 13 diamonds in the deck. The problem being, we just counted the jack of diamonds in both parts. Now, it's not a bad thing that we're saying we can draw the jack of diamonds. It just happens to satisfy both categories. The problem is we double counted. There are actually only 16 cards, not 17 cards, out of the 52 cards. Or basically, we should have a probability of 4/13 for an answer. What we have to remember is what's called the general rule. If 2 events are what we call mutually exclusive, they can't happen at the same time, such as a face card and an ace, or a heart and a diamond and a spade. They're mutually exclusive, then or simply means add. Or sometimes your book will call this disjointed. 2 events that can't happen at the same time. So again, you just add up the events, and we're good. For overlapping events, we need to add the probability of one event, the probability of another event, and subtract off what we call the intersection, the probability of A and B. So over here on part D here, I need to subtract off the probability that it was both a jack and a diamond. So we need to take off that 1 card that we've already double counted. Again, it's not that we're ignoring that card. It's just that we can't count it twice. So when we're looking at this and it says 452 and 13 out of 52, Well, the problem is that jack of diamonds that was in the first set shouldn't be in the second set. Or think of it more like 4 plus 13 minus 1, or 4 plus 12. There are only 16 cards. There's the jacks of hearts, clubs, and spades, and all 13 diamonds. Or you can think of there's all 4 jacks, and there's all the diamonds if you took away the jack of diamonds. Again, we already counted that jack. We just can't count it twice. So let's take a look at a couple other ideas that tie right into that. So again, the addition rule for probability is for the union of two events. The union meaning we're adding them together. If you think about a Venn diagram, that's saying, well, hey, if we took all the probabilities of A and B, or A and B together, right, we want all the things that would fall inside the circles. Well, the problem is the middle part would get counted twice. It's in the first circle, it's in the second circle. So we need to subtract it away one of those 2 times. I want all of circle A, but again, I can't recount this middle part. I need only the part without, right? I need only this piece sort of over here, right? By not counting that middle part again. If 2 events are mutually exclusive, again, if they're intersection, if A and B, if this middle part would have been 0, there's no probability of that. Again, the idea of drawing both a heart and a club at the same time. There's no one card that satisfies both categories. Again, we call that mutually exclusive or disjoint. And the probability would be just add the 2 probabilities, just add the 2 circles up. Because again, there's no middle to worry about. Take a second to think about the 2 questions here on the screen. Again, I'm going to pause the video now. See if you can't come up with a couple of answers. Alright, so when we're talking OR again, just a reminder for you, we've just been talking about the probability of being too loose or too tight for the pants example up at the top. Both of those would mean they don't fit. So again, what's the probability the pants don't fit? Well, they could be too loose or add too tight. So 0.1 plus 0.3 is 0.4. What's the probability the pants do fit? Well, again, an easy way to do that, if 0.4 is the chances they don't fit, then we want everything else. So again, 1 minus 0.4 would be 0.6. There's a 60% chance, or 0.6 probability, again, the pants do fit. Down at the bottom, now we've got a little bit of intersection. Again, the example up top was disjoint. They were separated. You couldn't be both too loose and too, fit at the same time. Think of it that way. Or fit and not fit all at the same time. Down on the bottom, though, you can need help in both. It says it right away. 55% of people need help in both areas. So when we think about that Venn diagram, that intersection, that middle part is 0.55. So I took 0.8, the probability they need help in math. So took off those who needed help in math and English. If you needed help in just math, that's 25% of them. Just English, same idea, 0.15. And again, the probability of not needing help in either, well, that kind of gets to our example at the left. What's the probability they need help in math, English, or both? Well, add up math and English, which you'll notice would have been way too large. That would have been 1.5. You can't have a probability that's greater than 1. But 1.5 minus the intersection, minus that 0.55, don't count it twice, would be 0.95. And it makes sense. 95% of people need help in math, English, or both. Down at the bottom, what's the chance that they don't need help in either? Well, again, take out those circles. What's left over in the box? Again, you just take your 1 minus 0.95, 1 minus the chances they need help in math or English or both, and we've got 5% or 0.05. Again, hopefully that helps you with the OR style of the question, right? That addition rule. What happens, though, if we're talking about AND? What if instead of a single event happening in multiple ways, one way or another, what if we said we were talking about an event where we're going to have 2 things happen? So down here at the bottom, we're going to draw a heart and a spade. What if I draw 2 cards out of a deck of cards? Well, now a very big idea comes up. The question of whether or not we replaced the card. Because again, if we draw a heart and a spade, well, the probability of drawing a heart, again, as we've seen previously, is 13 over 52. But now the question comes in, if I draw that heart, did I put it back? If I put the heart back, then the deck is back to the beginning. Got to reshuffle, everything's exactly the same as it would have been at the start, and the probability of drawing a spade would also be 13 over 52. So the probability of drawing a heart and a spade, well, that's where we go back to our multiplication rule. It goes back to sort of our rule of counting. If I'm going to do one thing and another thing, then I could just multiply the number of ways that those can happen. I can multiply the probabilities that those happen. So again, 1/4 times 1/4 with a little bit of reducing. This is going to be 1/16, or approximately 0.0625. Now, what if I don't put the spade back? Again, to draw them separately, with replacement as we call it, then we call this an independent event. The probability that you draw a spade is completely independent of what you drew the first time. It doesn't matter at all. We put it back. But to be a dependent event, the second event depends upon the first. So if I've already drawn a heart and I don't put it back, well, now the probability that I draw a spade, there are only 51 cards left in the deck. There's still 13 spades, but over here, the probability of drawing a spade, given that we drew a heart, well, again, there's 13 spades, but only 51 cards. That probability changed depending upon what we did here. So again, we call that a dependent event. A dependent event. Now, it doesn't really change a lot about what we're doing. 13 over 52, or 1/4, times 13 divided by 51, we're still multiplying. It's still the multiplication rule. But you'll notice that we get a slightly different answer, 0.0637 approximately. And again, we get that slightly different answer purely because, again, we've changed that denominator. In fact, we get a slightly better probability. The probability is a little bit greater because with that card missing, there's a better chance we draw a spade with fewer hearts to get in the way. Again, those are independent versus dependent events. Two events are independent if the likelihood of the second event doesn't change at all because of what happened in the first event. They're dependent if that second likelihood, that second probability does change because it came second because of what happened in the first one. Let's look at a couple more quick examples of this. So up top here, we've got drawing 2 marbles out of a bag of 8 total marbles. We've got 3 red, 3 blue, 2 yellow, without replacing the first one. So again, that without replacement idea means that I'm thinking this is a dependent event. We're going to be dependent. What's the probability that both marbles are red? Well, the probability the first marble is red is 3 marbles out of 8 marbles times, but now if I don't put that marble back, there are only 2 marbles that are red left out of the 7 total marbles that are left. So we've got 6 marbles out of 56 marbles, or basically, if we divide by 2, 3 of the 28 possible things that could happen. Now, down at the bottom, rolling 2 dice. Well, whether I roll 1 dice and get something should have no effect on what happens on the second dice. The 2 dice are completely independent. They're totally separate. So again, independent event. Probability of rolling a pair of 5s. Well, on the first dice, the probability would be 1 out of 6. That's one thing out of the 6 things that could happen. And the probability of rolling the other 5, well, the second dice doesn't depend on the first one at all. So again, that becomes a 1/6. And 1/6 times 1/6, the probability of rolling a 5 and another 5 is a 1 out of 36 chance. I hope that helps you with probabilities. Again, when they get a little bit trickier, remember that the multiplication rule basically comes from that AND rule. If you're talking about in one event and another one, again, the key word being AND, we're going to multiply the probability of the first event times the probability of the second. Be careful with that second probability. Is it a dependent? Does it change because of what already happened? Or are they independent, like the dice, right? With like the replacing the card. Does that second event not in any way change because of what happened first? And means multiply, though, whereas or, remember, meant add. And be careful with those overlapping events. Remember, add the probabilities, subtract away the intersection. Have a great day.